This conference will now be recorded.
So, hi to everybody, welcome. It's a pleasure for me to introduce the seminar. Nora Zannoni is a postdoc. She joined Isac Siena 2 years ago in the frame of active social infrastructure human capital project, and she's now she gained a temporary position in the frame of the TNRR project ITINERIS, and so she will talk about the VOC's measurement, and so she will talk much better than what I can introduce.
Thanks, Angela, and thank you all for being here today. So I will start with a brief introduction about my studies background and show you what is my main research interest, what I was working on before coming here, and what I'm currently working on since I'm at CNR. So I have a background in chemistry from the University of Florence. I continued to study chemistry in Copenhagen, in Denmark, where I got introduced to the...
Non si vede slide?
No. Sorry, there is a problem there. We can.
Did you share the?
Yes.
Così si vede, però se metti full screen.
Ok, però full screen non si vede qua.
Prova a mettere share the screen anziché la finestra.
Ok. Now we have some sharing. Share entire screen and condividi questo. Okay. Now. No.
Okay.
Okay, it's coming. Sorry. Okay, so I continued to study chemistry in the University of Copenhagen when I started to study atmospheric sciences as well, and I worked with a laboratory project on atmospheric aerosols. And I have a PhD in atmospheric chemistry with a laboratory and field project on OH reactivity measurements in the Mediterranean region conducted at LSE, which is a laboratory in France belonging to the CNRS labs. And during this project, I was building, characterizing, and optimizing an instrument to be used in the field for measuring the OH reactivity. And because this uses mass spectrometry, this was part of a network in Europe called proton-ionization molecular mass spectrometry. I had some working experiences before starting a postdoc of 5 years at the Max Planck Institute, where I worked on different projects, including the ALTO project and ICHER about indoor emissions, and I will show you something from this work later. And since 2 years, I'm at CNR, working on VOCs measurements in the Po Valley area and in Milan. So I started by doing some aerosol research, but my main research interest has been VOCs, volatile organic compounds, and I've been studying them under different aspects. One is the instrumental development with techniques, so the characterization of some techniques for measuring their concentration or the properties of VOCs. I've been working with the sources and sinks of VOCs, especially in this project, Charmex in the Mediterranean region during my PhD. And because one class of compounds is particularly interesting of the VOCs, I've been working a lot with biogenic emissions, so to look at the interactions between the biosphere and the atmosphere. These compounds can also be emitted from agricultural fields, and this is interesting to see, especially the impact that they have in terms of regional scale. I also I've been interested in looking at the whole ecosystem and how VOCs can influence animal behavior. And especially this project was conducted with ornithologists to see how VOCs can influence the orientation and navigation of birds. And this is a new emerging field of VOCs research, how human emissions can influence the indoor chemistry. And this is especially interesting because we are spending more than 90% of our time indoors. So we want to know the chemicals we are exposed to and how they interact with them. So the chemistry that they can bring, and what are the health effects also of these molecules. Last, this is not the newest research topic in terms of VOCs, because it's probably the first one that was started in terms of atmospheric sciences. But over decades of research, the atmospheric composition in urban areas has been changing a lot. So it's very important now to characterize how is this composition and what are especially the influences in terms of the health effects of these components. And I'm doing this now at CNR within the Reurbans project that connects to the actress infrastructure and, of course, to ITINERIS. So VOCs are trace compounds in the troposphere. They're very reactive, and they're present in the atmosphere in concentrations of ppb and ppt levels. That means one molecule of VOC over a billion or a trillion molecules of air. So it's a very small amount, but despite this low concentration, they're very important compounds. This because once they're emitted from natural and anthropogenic sources, they have an important role in the atmosphere, and they take part to oxidation processes, mainly initiated by the OH radical, that is the main oxidant in our atmosphere during daytime, but also ozone, which with a difference of OH is more selective. It prefers to react with alkene compounds, so those species having carbon-carbon double bonds, and also nitrate radicals and chlorine atoms. So these atmospheric processes are important because they lead to the formation of secondary organic aerosols and ozone, which have effects, very important effects on climate, but also on the air pollution and the human health and the vegetation health. So when we're talking about VOCs, what they are, we do not really know. There are thousands of different, or tens of thousands of different chemical species. This is what we think they are. In terms of global emissions, 90% of the emission come from biogenic sources, and specifically forests and specifically leaves. Half of these emissions is only one molecule. It's isoprene, so this is the most important VOC, let's say, not just because of its abundance globally, but also for its high reactivity with the OH radical, and also because starting from isoprene has a block, we can build the other biogenic VOCs that we can find in forests, like monoterpenes, sesquiterpenes. So monoterpenes is a class of isomers. It's those molecules giving this nice smell in the forest. And they are, it's a whole class of compounds with the same mass, and they are formed from 2 blocks of isoprene, sesquiterpenes from 3 blocks of isoprene, and so on, until here I reported a triterpene that actually we are not able to measure this molecule, but you can see it has lots of double bonds, so this reacts very well with ozone, very fastly, and we can measure well the oxidation products of this molecule. And this triterpene is nice to show because actually we have that on our skin, and also it's present on plant tissues. Anthropogenic VOCs, in terms of global emissions, make 10% of the abundance, but of course, if we go to the regional scale or the local scale, this percentage gets higher. And then there are the oxygenated VOCs. It's kind of a made-up class because they can be biogenic and anthropogenic, directly emitted or formed in the atmosphere from oxidation reactions. So when we want to quantify VOCs, we have lots of challenges. The first one is that they're that compounds in very low amounts, so we need very sensitive instruments to measure them. Second, they're very reactive, so we often have artifacts, or we need to develop a sampling system to avoid these artifacts. And sometimes the very reactive ones won't be measured easily. And then it's many different compounds with different functional groups. So it's not easy to measure them all with only one technique. So we need more techniques to be applied at the same time. And of course, when we go into the field, this is even more challenges depending on the environment where we're studying them. So if we look at the past 20, 30 years of research in terms of VOCs in the atmosphere, these are the techniques that have emerged to be the most spread and useful to quantify them as the individual concentrations. So starting from mass spectrometry, we can use PTRMS, that stands for proton transfer reaction mass spectrometry, or GCMS, that stands for gas chromatography mass spectrometry. So either we measure the concentration of these compounds individually, either we can use a top-down approach, and this approach was developed at the end of the 90s. It was considered to be very revolutionary back then, because the idea is the following: why do we need to measure every single molecule when we can use a property that these gases have in the atmosphere, that is to react all with the OH radical? The total OH reactivity is defined as the total OH loss rate due to reactive compounds in the atmosphere, and the concept is the following: we know quite well the sources forming OH, we know worse the sinks. We have different sinks, of course, in the atmosphere. Some we better know, others we don't. So we measure this total reactivity, that is nothing that the inverse of the OH lifetime, so it's a frequency. And then what we do is to calculate the OH reactivity from the measurements conducted simultaneously. And we do that by considering the sum of the products between the concentrations of the individual VOCs times the rate coefficient of reaction of them. And so we compare these two parameters, and in this way we can have some understanding of how much we know of the reactive gases budget. So once this approach was developed, the first publications reported that we don't know much. We actually don't know. We know very little, especially of forest environments. So this was one of the first publications coming from forest research, and they show that there was a lot of missing OH reactivity, but at the end it depends on how many molecules you measure at the same time. And these unmeasured compounds can be unmeasured because we lack the right measurement technique, because we measure but we couldn't identify them well, or because we do not really know what to look for. And then almost 10 years later, there were the first studies in the Amazon with OH reactivity, and they reported that during the dry season, this can go up to 90%. So there is 90% of this reactivity that we cannot explain. So this is one of the methods used for measuring the OH reactivity, and it's the one I've been using during my PhD. It's based on mass spectrometry, so we use a PTRMS as a detector. That's only one part of the system. And then we have a glass reactor where we dilute a reference molecule that we chose to be pyrrole for these reasons. We generate OH radicals inside the reactor, and then alternatively we dilute pyrrole with zero air, so air cleaned from any VOCs, or air having or ambient air, so air with reactive VOCs. And in this way, what we generate, and I'll show you with these steps, is a competition for the OH radicals between pyrrole and the reactive species in ambient air. So we measure these concentrations C2 and C3 with a PTRMS, and we determine this OH reactivity with this formula. It's quite easy, but actually when we go through the setup, this is quite complicated. You see PTRMS is only a small thing. In this, we first mix zero air, so we take air from the outside, we clean it with a catalytic converter, we dilute pyrrole with wet nitrogen, and we use wet nitrogen because we have a UV lamp emitting at 185 nanometers, and this photodissociates water vapors to generate OH radicals. And then, alternatively, we take only ambient air to dilute pyrrole, and so in this way we have these two concentrations. So this is how the system looks like in the field. And here I reported a review of the different measurements of OH reactivity conducted in the world. So you can see in red, it's the places, the environments where the OH reactivity measured was above 50 per second, so a very high value. That means a lot of reactive compounds in the atmosphere. And I reported also the different sites, and you can see that a high reactivity was measured either in big megapolis like Mexico City, New York, Paris, Beijing, either in forest sites or in the Mediterranean basin as well. So this is where I'm starting now to talk a bit more into details. So this project is focusing on the Mediterranean basin because we all know it's a crossroads of pollution for the particularly atmospheric circulation, and then an intense local anthropogenic activity, local biogenic activity, and polluted air masses meeting all in the Mediterranean basin. And these bring to a very high loadings of gases and particles and a complex chemistry. So for this reason, it was funded the CHARMEX project, which was a big project conducted in the years of 2013. So in this project, we used the OH reactivity to constrain the reactive gases budget at one site of the different field sites that were measuring during that time. There were different field sites across the western and eastern basin, equipped with advanced instrumentation to have very intensive measurements in the air composition. And we chose this site. So in this project, we're participating different French institutions, also Italians. This site was chosen for being free from local anthropogenic pollution, so we could better see receive their masses coming to the site. And this is what we measured. So you can see the OH activity in black measured was reaching maximum 17 per second. It's increasing when the temperature is increasing and has a distinct diurnal profile. And also I reported the contribution in terms of reactivity of the different classes of VOCs that were measured simultaneously at the site, and also the origin of the air masses. And you can see that when the air masses were coming from west or south, we had the largest missing OH activity, so the most unexplained reactive gases. So this is all the VOCs that were used to calculate the OH activity. And you can see many anthropogenic VOCs and very few biogenic VOCs. But what we saw is that during daytime, the biogenic VOCs contribution was the largest at the site. During nighttime, when biogenic emissions decrease because we do not have any light and we have lower temperature, other compounds such as the inorganic molecules or the oxygenated VOCs were more important. So we started to look specifically at this class of biogenic VOCs. To see what was the missing reactivity. And we actually used a very simple model to look at the oxidation of some of these VOCs. So we took the period when the temperature was highest, and we used the oxidation schemes of reaction for alpha-pinene, isoprene, and limonene, and this is the output that we have in terms of OH reactivity. And you can see that alpha of the species is actually the biogenic VOCs, but the other alpha are oxygenated molecules such as aldehydes, isoperoxides that we did not measure. So these oxygenated compounds explain partly the missing reactivity that we could explain. Of course, it was 10 years ago. I guess if we go now to the same site with the techniques that we have, maybe we could even explain very well with the measurements this gap. So we conducted more measurements in the Mediterranean, in a forest site in the south of France that is known for being an isoprene emitter. So as we could expect, of course, the contribution of biogenic VOCs is even larger. But if we put these results in perspective of all the studies of the OH reactivity conducted at forest sites, we can see that the place in Corsica, that is this here, that it was not a forest, it was supposed to be free from local anthropogenic pollution, but still it's having an OH reactivity as high as temperate forest or boreal forest sites. While the forest site in the Mediterranean region a reactivity almost as high as a tropical site. And this was for the abundance of isoprene at the site. So biogenic VOCs, it's an important class, so for this reason I wanted to go and study them in the place where there are most of them. So where the emissions are highest, that is the largest contiguous forest existing on Earth, it's the Amazonian rainforest, and I joined this project APTO with the Max Planck Institute. APTO is a project that is 50% funded and led by the Max Planck Institute for Biogeochemistry, and 50% funded and led by INPA, that is the the National Institute for Amazonian Research in Brazil. And the goal of this project is to build a research infrastructure that is a field site in the middle of the Amazonian region, in a site that is considered for being pristine. Pristine, it's a big word now in the Amazon forest, but the important is that what is important to say about this site is that the dominant direction of the air masses is the northeast sector, which means that the air masses are passing above a large portion of the forest, and they avoid big cities such as Manaus. So we can really look there at the atmosphere without the influence of anthropogenic emissions. So the site is northeast of Manaus. In there, now there are, I guess, the best instruments you can find in the market all together. So it's a very equipped field site with lots of measurements and lots of projects going on. Among these, there is a tall tower. This is 325 meters tall. It's 1 meter taller than the Eiffel Tower, so it's quite high. It's kind of unique infrastructure that is used for measuring the atmospheric composition, so VOCs, particles, but also meteorological parameters. And so I started the VOCs measurements from the APTO tower. This was because it was just finished to be built when I joined the project. And for these measurements, we selected 4 sampling heights. The shortest one was the one closest to the canopy height, so 40 meters, until 320 meters. And there we installed these automatic samplers. Why we did that? They are 4 samplers identical to each other that were chosen to be installed there at the height. This because we wanted to avoid long sampling lines, because we wanted really to look at the very reactive biogenic VOCs, and specifically at these classes of monoterpenes and sesquiterpenes that are isomers and that cannot be distinguished with normal PTRMS measurements. So in there I went every day to install samples, remove samples, collect samples, a lot of samples, and then I brought them to Germany where we had a GC-TOF MS. So one sample looks like this. There is some sorbent material that traps the VOCs, and then with the desorber we can desorb them in a GC-TOF MS, so a gas chromatography mass spectrometer. It was a special one because it's equipped with a chiral column. So these are normally measurements not really done in atmospheric labs. It's more done in pharmaceutical industries or perfume industries. Because we really wanted to differentiate also within the optical isomers. So not just the isomers, but also the chiral ones. So we developed a method for doing that, and you see from all these peaks we could extract very well, and we have a very good resolution of the peaks of the chiral monoterpenes. So in terms of monoterpenes, these are results from 2 seasons. You can see that day or night, wet or dry season, there is one compound that dominates in terms of concentration, that is the mannose-sulfapynin. So if we look at the DL profile of the 2 most abundant ones, you can see that first concentration are higher during the dry season, but also they have all a diurnal profile changing with light and temperature. If you look at the sesquiterpenes, the situation is a bit more complicated. First, there are many, many different compounds. It's very hard to find the standards to identify them. And there's very little research on these compounds because they're also very reactive, so it's not very easy to measure them. So we have more diversity here in these pies. You can see differences during wet and dry season, during day and night. And here I reported the ideal profile of one of the compounds that was always present in the samples, that is this alpha-copain. So it also has a diurnal profile. You see it varies with light and temperature, just like alpha-copain. But then I looked at the four most abundant ones, and I reported their concentrations here together with temperature, light, humidity, and this stomatal conductance. That is a measurement that you conduct at the leaf level. And you see when the stomata are opening, if we have a covariation of concentration, it means that these VOCs could come from leaves. And we see these in the first two graphs, A and B, but we don't see these in C and D. They actually have mirrored profile. So we went to look for more sources of emission. These were samples taken at 80 meters, so quite high. And I started to take samples even in the understory, which is 20 centimeters high. This includes everything: soil, litter, mushrooms, mosses, lichens, everything. And actually we saw that these molecules that had this mirrored profile were more abundant in these samples. So we have many different sources, but we consider leaves always to be the most abundant in forest. And so we went to look also to the chiral VOCs. If you're not familiar with chirality, just think about your two ends. So these are not superimposable, just like chiral molecules. Chiral pairs have the same physicochemical properties, so you would wonder why we're interested in measuring them. Because they have a different biological activity, especially in terms of nasal receptor, which is what we are interested in terms of VOCs. So our nasal receptors and the nasal receptors of animals perceive them differently. So if you take one of the most common monoterpene, that is limonene, the plus limonene is smelling like oranges, and the minus limonene is smelling like turpentine. So they have a distinct smell. Globally, it was found that alpha-pinene is the most abundant chiral molecule, and it was also found that it was region-specific. So the boreal forest was emitting more plus, and the tropical forest was emitting more minus. So we wanted to see what was going on in the Amazon in our samples. And what we found is, you see the red line is the plus alpha-pinene, the blue line is the minus. In terms of concentration, they're higher at the bottom level, as we would expect, closer to the canopy, and they decrease with height, as we would expect from atmospheric oxidation or atmospheric dynamics. But actually, we would not expect that there were changing concentrations between them. Indeed, if we take the chiral ratio, so the minus alpha-pinene divided by the plus, you can see that there is a tenfold increase in this ratio. So we wanted to know why was this happening, and we looked at the ideal profile. And you can see that depending on the height, the two compounds show different profiles. So we started from this height at 80 meters, that is this one, sorry. Yeah. So here I reported with the concentrations, also the temperature, the photosynthetic active radiation, and the stomatal conductance that I was telling you, is measurement done at the leaf level. So you can see that the two compounds start when light and stomatal conductance by consequence is increasing, and but the concentration of minus alpha-pinene is sustained during the day for an increase in temperature, while the plus alpha-pinene is not increasing with temperature. And indeed, we saw that there is a temperature dependency in these emissions that goes more in favor of minus alpha-pinene. This is why we see more minus alpha-pinene at higher levels. And then we went to look to those compounds where the plus was larger than the minus, so the red area there, and we looked for some other tracers. And some important tracers of VOCs when we're talking about mechanical damage of plants are these green leaves volatiles. This is a group of molecules including aldehydes and alcohols, and it's basically this smell we have when someone is cutting the grass. So we saw that these concentrations were increased. When these were increasing, also the plus alpha-pinene was increasing. So plus alpha-pinene might be also a tracer for this process. And then we looked at these profiles that we were measuring at 40 meters. And because this level was really close to the trees, we were wondering if other effects could have influenced these samples, and so if it was a local effect only. And indeed, we looked for another tracer, indole. It's a tracer of herbivore attacking the leaves. This elicits emissions of monoterpenes and sesquiterpenes. It was found in the lab, and we see something similar in our samples, so this could be an explanation. But also there were so many nests that I started to take samples at the nest, and we saw that actually nest emissions emit more plus than minus. So this could also be an explanation. So actually we could distinguish different effects and different processes by taking the two compounds separately. That is something that normally is not done, because normally they're measured all together, or sometimes all together as a class of compounds. So if we go in very detail, we can distinguish different processes happening in the forest, where leaves is considered the most important compartment of emission. So, of course, when we're taking samples of VOCs, we wonder also if we have an influence in that, and if we can contaminate that with our smell. So from these, we started to think also if us as humans, with our emissions, we can impact the atmospheric chemistry. And this brought to the beginning of a new research field at the Max Planck Institute in the group where I was working before. So the first deployment, the first question was if us, as humans, when we gather all together outside, we can have an impact to the atmospheric chemistry. So for doing that, they brought the instruments to the place in mines where there was more people gathering together, that is the football stadium during a match, and what they measured was actually a very high concentration of ethanol coming from the consumption of alcohol during the match, exhaled from people. So you see how ethanol is varying with CO2 that was measured at the same time. You see very well the graph from the two times of the match here, and ethanol staying in the stadium also when the people left. So almost 400, 500 ppb of ethanol. It's a very high value. That means, yes, we have an impact to the atmosphere, at least locally. And then we wanted to know what is our baseline emission. So without consuming any drinks or without eating or without any activity. So from this, it was funded a big project called ITINERIS, and this was one of the first results of this project. This pie reports the contribution in terms of concentrations from the whole body of different volunteers. So it's a statistic here, result. You see that the main VOC emitted from people is acetone, and then we have isoprene, methanol, and some oxygenated VOCs. Acetone, isoprene, and methanol come from our breath. So breath is the main source of VOCs from people. Baseline emissions, in this case. And skin is another important source of emissions. And we wanted to see how these influence the indoor chemistry. So we conducted different experiments in a stainless steel chamber where there were sitting 4 volunteers, 2 males and 2 females, about 25 years old. This room is climate controlled, so we can control temperature, humidity, and the air ventilation. And of course, the volunteers were following a very strict experimental protocol, like what to wear, how to wash, and what to eat. So that we could not have any interference on their emissions. And you can see here, outdoor air was entering inside the room, cleaned, of course, from particles and VOCs. And a part of the experiment was without oxidants, so just the 4 people. And a part of the experiment was done with ozone. This because we wanted to see what was happening when ozone was present in the room, because ozone is considered to be the most important oxidant indoors. And the main source of ozone is the outdoors. So ozone infiltrating from the outdoors, coming indoors. So of course, it depends on how much ozone also we have outdoor in the atmosphere. Yeah, from the air exhaust, we were measuring VOCs, OH reactivity, CO2, ammonia, ozone, particles, different things. Then all the results were, all the measurements results were input in two models, first a kinetic model and then a computational fluid dynamics model. These are very, I won't have time to talk about these models, but they're very interesting as well. So if you are interested, there is this, yeah, you can read this paper here. So this is what we measured for the OH reactivity. You can see the results from a benchmark experiment. So for people at moderate temperature, low relative humidity, wearing a longer clothing. So at first we measured only the empty chamber, and then we had 4 people without any oxidant, so no ozone, and then 4 people with ozone, and then the 4 people left the chamber. And you see, this is when we were taking background measurements here. If you remember that pie I showed you before with the concentrations, acetone was the dominant compound. But actually, when we are talking about OH reactivity, you have to think on how much these compounds are reactive to OH. And indeed, without any ozone, the dominant compound is again isoprene. So it's a very important compound, as you see. Isoprene coming from breath. So breath is the main source of reactivity. When ozone enters the chamber, we have that the reactivity doubles, so it's higher. And we have a high contribution of carbonyl compounds, including 6-MHO, or OPA, geranyl acetone, and more aldehydes. These are all molecules coming from the ozonolysis of squalene, so of the ozonolysis of our skin lipids. We know very well among these lipids, one of them is the squalene, and we know how this reacts with ozone. So we form all these molecules that are also reactive to OH. So without ozone, breath is the main source of reactivity. With ozone, skin is the main source of reactivity. Now, from the measurements of the OH reactivity and those of the calculated reactivity, we can see if we covered the whole reactive compounds present in the room. And this was the case. So we measured all the alkenes present, and we know that alkenes can react again with ozone, and through the formation of some Krieg intermediates, forms OH and other compounds. So we could determine how much OH is formed from these reactions. And we did that by considering the ratio between the OH production rate and the OH loss rate. The OH loss rate is what we measured as OH reactivity. The OH production rate can be determined from the concentrations of the alkenes, of the ozone that were all measured, and from the rate coefficient of reaction of these compounds with ozone that can be found in literature, and the OH yield that can also be found in literature. So what we saw, and you see here with this method, it's the concentration of OH that was actually through the different experiments that we repeated on 3 different groups of volunteers, and with replicates experiment, we found a very reproducible concentration. That was also confirmed from a second method that we applied, that it's using the ratio between isoprene and oxidation products of isoprene. And what we found is that the OH formed from this reaction, so only 4 people present in the room with ozone, it's almost 1 times 10 to the 6 molecules per cubic centimeters. So this value, if you're familiar with OH, it's the same concentration that we consider globally outside in our atmosphere. So it's a substantial value if you think that here the source is 4 people and ozone. And also another important point is that, of course, we need both to have OH. So without ozone, we do not measure any OH. So we need ozone and the 4 people as well. If we look at the contributions from the different alkenes to the OH formation, 6-MHO is the most important molecule this time. So if you remember the graph with the OH activity, 6-MHO was also there. That means that this is a key molecule because it behaves both as a sink and as a source of OH at the same time. And you see here the 6-MHO and the other species present. Most of them come from our skin reactions. So the contributions to OH formation comes from our skin. If we evaluate these results and our study with different studies conducted on OH from experiments and model estimates indoors, none of them considered the presence of people, so this differs compared to the other studies for this reason, but they all came, so they considered the different sources of OH, for example, using cleaning agents, where alkenes are very highly concentrated, or considering the photolysis coming from outside. So they came to similar concentrations. So since we consider the people, we can consider that the indoor environments can have all these sources together. So actually we can come to a quite high value for the OH concentration indoors. And this is a very interesting result because we always consider the indoor chemistry very different from what we have outdoors because of reduced sunlight. So we consider that ozone is the most important oxidant. Now I'll come to the last part of the presentation. Hope you're still following. And this is what I'm currently working on now at CNR. So we are looking at the urban atmosphere. We know that the air pollution is one of the causes of premature death in Europe, but we also know that this number decreased in the past 20 years due to declining concentrations for improved quality policies. But still, 70% of the European population lives in urban areas, and 97% of this population is still exposed to very high values of PM 2.5, so higher than the guideline level of 5 micrograms per cubic meter. That is the updated guideline from WHO. So this means that despite the urban atmosphere has been changing with the years for these policies, there's still a urgent need to characterize this air composition and to evaluate the air quality policies and the health effects of these compounds in Europe. So from these reasons, it was funded from the European Union, the project Urbans, that was granted also to CNR, Isac, and this connects with the actress infrastructure. So it uses the knowledge and the expertise, the infrastructures and instrumentations from actress to support the local air quality monitoring network to better characterize, to have intensive measurements of the air composition. And one of the working package was to conduct these measurements in real time in different pilot cities in Europe, and one of the cities was chosen to be Milan. Milan because we know that it's in the Po Valley, that it's a hotspot for air pollution. This is an article of this year from The Guardian. Yeah, this is from some time already. And Milan is also the most polluted city in Italy. So in there, we installed our instrumentation, and especially what I'm talking about is these measurements from the PTRMS. This is an instrument that was bought for the actress infrastructure at Montecimone, and it will be installed there in 2025. At the moment, it's installed in this mobile trailer, which is parked at the CNR area in Milan, which is close to the university campus, since 1 year. So, very briefly, because I've been speaking about this technique, but I haven't said what it is. So this on the right is our instrument, which is the latest model of this technique that was actually developed in the 90s already. Very simplified, we have a discharge, and from a water reservoir we form protons. These are used as primary ions, and they react with the VOCs entering inside the instrument, having a proton affinity larger than water. So only these VOCs will be able to uptake a proton, get protonated, ionized in this way, and they will be traveling in a drift tube thanks to an electrical field that is applied, going to a mass analyzer where they're separated according to the mass to charge ratio, and then finally a detector that converts the ion signal in electrical signal. So the revolution from this technique is to use this method to ionize the molecules, so a soft fragmentation, soft ionization, to have the least possible of fragments, and in this way to make, let's say, the analysis of complex sample easier. Of course, we still have a lot of peaks, so it's not that easy. And this instrument is a Vocus CI-TOF. It's based on this technique. It's a very powerful instrument with a very high sensitivity and a very good mass resolution. So we can distinguish compounds with masses, even differences of 5 digits. And we are looking at the spectrum of from 0 to 500. So we have a lot of information, and this is acquired in real time also. So we measured, of course, several anthropogenic VOCs. I won't go too much in details, several biogenic VOCs as well, and oxygenated VOCs. And now I'll focus a bit on these DL profiles. So here I reported 4 anthropogenic VOCs and 4 biogenic VOCs. You see very well that with the anthropogenic VOCs, we can distinguish 2 main peaks, one in the morning and one in the evening, corresponding to the rush hours from traffic. And then the concentration is decreasing during the day. If we look at the biogenics, they have some similarities because the concentration of these molecules is also decreasing during the day. We have this main peak in the morning, but this could be due also to, as we saw in the forest, to light and temperature. Now here I reported the same concentrations during 2 seasons, wintertime and summertime, of our measurements, but normalized by their midnight concentration. And I reported 6 different VOCs coming from different sources and having a different OH reactivity. So they're sorted from the most reactive one, that is the sum of the monoterpenes, to the least reactive, that is D5. So what we would expect is to see a difference in here if the OH reactivity was an important process explaining this decreasing concentration during the day. But actually, we do not see much difference. So it seems that atmospheric dispersion here is the main driver of this decrease. If we look at the summertime data, we can see some differences, but this could be explained from a continuous and a higher emission of the biogenic compounds, so monoterpenes and isoprene during the day. And if we look again at the biogenic VOCs, I reported here isoprene, the sum of the monoterpenes, because we cannot go too much in details with the PTRMS measurements, and D5, that is a siloxane. D5 is emitted from personal care products. And I reported these DL profiles because it looks like the monoterpenes can be, similar also to D5 and isoprene, both of them. So maybe it comes from different sources of emission. And this because it was recently found from studies conducted in the eastern US with a mobile lab going through measuring the air composition in highly populated areas. They saw that personal care products contributions in highly populated area, they contribute to the ozone formation equally than fossil fuel combustion products. And especially they saw this with the siloxanes and monoterpenes. So it can be that what we see in Milan as well is reflecting this finding that was already seen in highly populated areas in the US. So with this, I wanted just to show you that despite the urban atmosphere can sound like an old topic, it's still very interesting to study because there has been many changes with the years, and especially we can see with the new techniques also some emerging compounds having importance. And finally, thank you for some acknowledgement, sorry. So from the in the order of presentations of these results for the contribution that I received for these results coming from my supervisor during the PhD and our group, Jonathan Williams at the Max Planck Institute and the group in Mainz, and of course Angela and the CNR team as well. And thank you for your attention. Yeah. Hope it was not too long, but it was quite long.
Any question from here or from people?
Okay.